line, yeah. In this figure, it seems that the gray area extends to zero density.
Yes, zero chemical potential, yes.
In the next graph, it seems that you are predicting some additional critical point in the red.
Well, yes, so what we're seeing there is the crossover. Okay, that's what we've actually seen. Oh, sorry, went too far. Okay, so the conjecture is that that crossover region then becomes a phase transition. Okay, there's crossover here, which I haven't marked. And then there's a critical point and a phase transition. That's a conjecture. Okay, does that answer your question? Okay. Any other questions? Okay. All right. So what we'd like to know is what's going on in the phase diagram. What should we expect in the phase diagram at the very highest densities? So at the very highest densities, what are we doing? We're starting here with nuclear matter, neutrons and protons, all next to each other, and we're compressing it further. We're pushing the neutrons and protons closer and closer together. So let's just imagine what that's like. So here is nuclear density. Nuclear density is 0.17 neutrons or protons per cubic Fermi, cubic femtometer. So here's a picture of what that looks like. Okay, this is 1 over 1.8 cubed. So they're about 1.8 Fermis apart. And each neutron or proton has a radius. It's not sharp, but roughly speaking, 0.8 of a Fermi is a reasonable sort of estimate for the radius of a neutron or a proton. And you can see, or you put them together, and you've got a little bit of space between them. They're, roughly speaking, you can distinguish one neutron from another neutron, right? They're next to each other, but they're not overlapping. So if I ask for a given quark, which neutron is it in? You can say so. You can say which neutron it's in, right? It's clearly, it belongs to this neutron and not that neutron. So that's nuclear matter. And this is the density of the nuclei inside you, right? You, what are you? You are a sort of mist of little droplets of nuclear matter with electrons in between, right? That's you. You're a mixed phase with little droplets of nuclear matter and electrons sort of buffering them. So in the little droplets of nuclear matter inside you, they look roughly like this, right? They're at nuclear density with the neutrons and protons next to each other, but not overlapping. Now, if we suppose we imagine compressing this like maybe 6 times nuclear density. Okay, so 6 times 0.17 is 1. So this is now 1 neutron or proton per cubic Fermi. And if you draw what that looks like, their radius is still 0.8 Fermis. So you draw them next to each other, only 1 Fermi apart, and you find they're now overlapping very strongly. So now if I ask you, here's a quark, which neutron or proton does it belong to? It's really not so clear which one. So this is where we start thinking this is not naturally described as nuclear matter, a liquid of neutrons and protons. It's really looking more like quark matter, a liquid of quarks. And the grouping into neutrons and protons is no longer playing a significant role because they overlap so much. So this is not a very sharp distinction, but it's reasonably clear what the difference is here. So we're interested in quark matter. We're interested in pushing up to the high density end of that phase diagram and asking ourselves, how are these quarks going to arrange themselves? So we're pushing lots of quarks into a box, right? You could just think of it as, here's a box and we stuff in lots and lots and lots of quarks to this density, and we ask, how do they arrange themselves? So here is a story about what happens when you compress fermions. Quarks are fermions, right? They obey the Pauli exclusion principle. So what happens when you compress fermions? So let's think about quarks are the fermions in this case, but the story I'm going to tell you is very general, and I'll emphasize that as we go along. So first, let's imagine we go really high density, okay? Super, super high density, way beyond 6 times nuclear density, very high density. So at very high density, so we're looking at this area in the phase diagram out here, right? Far out, low temperature, very, very high chemical potential, very high density. So we know that the main interaction between quarks, QCD, gets weaker when the energy transferred gets higher. So we can think of these as weakly interacting quarks if you're at high enough density. So let's think of them as weakly or almost free quarks. So if you have a system of fermions that are free, let's say, let's start with free, and then we'll add in the interaction later. So let's start with free quarks. What happens with a system of free quarks? Well, we learn this at some early stage in our studies of quantum mechanics. They just fill up the free particles in a box states, right? And that's what we call filling up the Fermi sea. So here I'm showing this in momentum space. So horizontally, I've got the x component and the y component of the momentum. And vertically, I've got the energy, right? So here you have fermions, quarks in this case, with momenta pointing this way or this way or this way. And yes, and doesn't matter which way they're pointing, the energy only depends on the modulus of the momentum, the length of the momentum vector. So those all have the same energy. So they form these circles, since I'm only showing 2 dimensions of momentum, just to be able to fit on the screen. So they fit on these circles. In 3D, it would be Fermi spheres. And you fill up all the states up to some energy. And that's the Fermi energy here, which at 0 temperature is the same as the chemical potential. So, okay, this is the story with very weakly interacting quarks, let's say free quarks. You just fill up the available states from low energy to high energy, and that corresponds to filling up states with low momentum to high momentum. All right, that's good. Now let's start allowing the interactions back in, right? What happens to this when we take into account the fact that quarks have interactions? And specifically, we know what's going to happen when we lower the density. They're going to confine into hadrons, so there must be some attractive interaction between quarks. So what happens if we allow our quarks to have attractive interactions? Well, there's this very general result that any attractive interaction between two fermions will cause a rearrangement of this Fermi surface known as a condensate of Cooper pairs. And that's the mechanism of superfluidity and superconductivity. So this is a very important piece of physics that lies behind an awful lot of things in ordinary terrestrial condensed matter physics, as well as potentially in neutron stars. So what is going on here? What is this rearrangement of the Fermi surface, and why does it happen? Okay, so that's the next thing we're going to talk about. So now I'm going to look sideways. Here I'm looking sideways on at that cone. So I'm seeing all the states with momenta pointing in different directions, all having the same energy here. So what is this condensate of Cooper pairs, and why does it happen? Well, it's called the BCS pairing mechanism, Bardeen-Cooper-Schrieffer. And it says that when there's an attractive interaction, the system will look at that bare Fermi surface with all the states up to the Fermi energy filled and all the states above empty, and say to itself, that's nice, but I can make the energy lower by throwing in some extra particles. In particular, it throws in Cooper pairs. So this is a pair of particles on opposite sides of the Fermi surface. So with momentum k and momentum minus k, these two guys form a Cooper pair. And it does it below the Fermi surface too. It creates holes. Where there were previously particles, it creates pairs of holes, one with momentum k and a partner with momentum minus k. And it does this in all the momentum states to some degree or other. Okay, so that's the nature of the state. That's the picture of the state. Some sort of set of pairs of particles created above the surface and some set of pairs of holes created below the Fermi surface. And this, as I said, is very general. This applies to any system of degenerate fermions with a Fermi surface, with an attractive interaction. So it could be electrons, which are fermions in a metal, which is just basically a box of electrons. It could be helium-3 atoms, which are fermions in some sort of, atomic trap or something. It could be neutrons in nuclear matter. Neutrons themselves are fermions. So even before we get to quarks, the neutrons in nuclear matter could be doing this. And it applies, we would expect, to quarks in quark matter. So let's go beyond the picture here and say, what sort of state is this? What does it look like? So here's a way of understanding this BCS state. I'm going to write it in a many-body language here. So what is the BCS state? You start with the Fermi sea, everything up to the Fermi energy filled, everything above empty, and then you hit it with some operators to make the BCS state, which has lower energy. And what do those operators look like? Well, it's a product over all momentum states, all momenta below the Fermi surface and all momenta above the Fermi surface. And in every momentum state above the Fermi surface, you've got two terms here. You say there's some probability that I'll just leave that state momentum alone and not do anything. And there's some probability that I'll create a Cooper pair. This A dagger P creates a fermion with momentum P, and this A dagger minus P creates its twin on the other side of the Fermi surface. They're created together. So in each momentum mode, you've got a superposition of nothing happens in this momentum mode versus, plus some probability here, this sigma P, that we have a Cooper pair in that momentum mode, a pair of fermions. And similarly, below the Fermi surface, for the lower momenta, in each momentum, we say there's some probability, some amplitude, I should say, really, because this is a state, some amplitude that we leave that state alone, and some amplitude that we create a whole pair there. And so we start with the Fermi C, we act on it with this product of many factors, allowing us to either make a pair or not, and that's the BCS state. And these sigmas here are variational parameters, or sigma and rho. So you just vary those numbers to get the lowest energy, right? This is a variational family of states. And you explore, you vary the sigmas and the rhos until you get the lowest energy. And what the BCS mechanism says is you will find some values of those coefficients that will give you this BCS state having a lower energy than the Fermi C. If you have an attractive interaction, you will find a more favored state than the Fermi C. And it'll be the attractive interaction that makes that happen. Any question about this construction, many-body construction of the BCS state? Everybody happy with that? Okay.
Correspondence between UV and then sigma, usually then people use notation U and V and then
For those coefficients?
Yes.
Okay, I use sigma and rho, I guess. Okay, what can I say? Yeah, maybe U and V would be better. Okay.
The requirements of the attractive interaction.
Yes, you need an attractive interaction, and then so let's go on to why. Okay, I think on the next slide, if I remember rightly, we'll be. Oh no, okay. So let me go back and say a little bit word about why then. Okay, so why is this going to work? Well, it doesn't cost you any energy to create. Let's say you create a particle here and a particle here. It doesn't cost you very much energy to create a pair of particles because they're close to the Fermi surface. The free energy is energy minus chemical potential. So the energy since the energy is the chemical potential here at the Fermi surface, it actually costs you zero free energy to make a particle. Another way of thinking about it is that you can take a particle down here and move it to just above the Fermi surface, so create a particle-hole pair, and that doesn't cost you very much at all. You can make it a very small energy cost. So you can make these particles and these holes near the Fermi surface for free, basically. It costs nothing. So if there's an attractive interaction between them, that once you make them, they feel an attractive interaction which lowers the energy, then you've found a way of lowering the energy, right? And it's because you have all this phase space at the Fermi surface that's zero energy phase space. That opens you up. It means you've got the possibility of doing things, right? It costs you nothing to make particles near the Fermi surface or holes. And if you make them in a way that feels an attractive interaction, then the energy will go down. So it's sort of like being given stuff for free and then you can go and sell it on eBay, right? You can always make money that way. Okay. So let's talk about what happens now. So imagine multiplying out that. I'm sorry to keep going back and forth, but so imagine multiplying out that BCS state. So you're going to get something with the Fermi C plus things with 2 particles, things with 2 holes, things with 4 particles, things with 4 holes. Let me go back and make that very clear. So if you imagine multiplying out these factors here, if you multiply out these factors, then there's one. In each factor, you have to choose, do I take the 1 or do I take the pair creation or pair or whole creation part of it? So there's one term when you multiply this all out where every one of these factors, you take the 1, okay? And that's just going to give you back the Fermi C. And then the next thing there is a contribution that you add to that, where in every momentum mode, you would take the one, except in one momentum mode, you take the I make two particles. And there's another factor where it's one from all of them, except in one momentum mode, I do the create two holes. And then you can see that there's ones where it's one from everyone, except I create two, I have two momenta where I create a Cooper pair, and two momenta where I create. So that's what this is saying here, right? That when you multiply that out, you'll get your BCS state is a superposition of the original unmodified Fermi C plus a state where you made one Cooper pair, plus a state where you made two Cooper pairs, and so on, plus a state where you made a Cooper pair of holes, plus a state where you made two Cooper pairs of holes, and so on. So it's a superposition of all these states. That's what it's going to look like, okay, with some coefficients. Now, we can see some interesting things already just by looking at this. Because what do you see here? This state is not an eigenstate of fermion number, right? The Fermi C has a definite number of fermions, but this state has two more, and this state has four more. This state has two less. This state has four less. So the ground state in this case, since we're saying it's the favored state, right? It's the lowest energy state, so it's the ground state of the system. It's not an eigenstate of fermion number. It does not have a definite fermion number. And that means that when you construct your excited states, you build the spectrum, right? That's what you do, right? You start with the ground state, and then you hit it with operators to create the spectrum of the remaining states. Those states, they're built on this state. They're not going to be eigenstates of fermion number either, right? You build stuff on top of the vacuum that isn't an eigenstate of fermion number. It's not going to be an eigenstate of fermion number. But we didn't do anything to the Hamiltonian, right? The Hamiltonian conserves fermion number. Here it is, right? You know, H commutes with N, right? The Hamiltonian commutes with the fermion number operator. So the dynamics doesn't know that we did anything, right? The dynamics still conserves fermion number. So the dynamics still says, you give me a state with 300 fermions, and I will evolve it forward in time, but it will always be a state with 300 fermions. That's what the Hamiltonian is doing. So it's still true that if you evolve this state forward in time, this this Fermi C plus 2 state will evolve into a Fermi C plus 2 state. The Fermi C will evolve into a state with however many fermions the Fermi C had. This state, each of these states individually will evolve according to the nice number-conserving dynamics of the Hamiltonian. But because the state you start with is a superposition of all different fermion numbers, the state you get after evolving will be a superposition of all different fermion numbers. So basically, fermion number conservation isn't helping you, right? Normally, you can use it as a constraint of some kind that, oh, well, we had this as the input, so we can say something about what it evolves into. But now you can't say anything. And so, you know, you might do this as a sort of, you know, goofy, fun equation that spontaneous symmetry breaking is the same thing as the famous garbage in, garbage out principle. Okay? Yes, you may have a beautiful mechanism, but if you feed rubbish in at one end, you will get rubbish out at the other end, no matter how beautiful and pure the mechanism is that processes it. In this case, that mechanism is the Hamiltonian. So this is spontaneous symmetry breaking, right? When people say fermion number or some other symmetry is spontaneously broken, this is what they mean, that the dynamics preserves the conservation law, but the input states don't, and as a result, the conservation becomes rather meaningless. Now, another way of talking about this state, another interesting feature of this state, is that if you construct a field that corresponds to the Cooper pair, so this is a field, we're calling it phi, that says I make or destroy a fermion with momentum k, and I destroy a fermion with momentum minus k. So this you could think of as the operator that makes or destroys a Cooper pair. This operator has an expectation value in the BCS state. Normally, you'd think this operator would have expectation value 0, because between eigenstates of fermion number, it changes the fermion number. So if you start with a state with 300 fermions, you act on it with this operator, it'll turn it into a state with 298 fermions. And then if you ask what's the overlap between that and the original state, the answer is 0, because they have different number of fermions. But in this case, this state already has a mess of all different numbers of fermions. So you put this operator in between two BCS states, and it just takes, let's say, the one with two particles here, that this operator gets rid of the two particles and makes the Fermi C, and the Fermi C then has an overlap with the BCS state. The BCS state includes the Fermi C. So this operator that changes the number of fermions has a non-zero expectation value in the BCS state. Whereas in the ordinary sort of the perturbative vacuum, the pure Fermi C, okay, in that state, its expectation value would be 0, right? Because it tries to change the number of fermions. So you can also picture this spontaneous symmetry breaking in terms of how the expectation value of the fermion pair field affects the energy. So here's a classic picture, the classic wine bottle picture, where this is in the horizontal direction, we have that fermion pair field, the real and imaginary parts of phi, okay? And vertically, we have the energy. And so phi equals 0 is the original Fermi C, and that's a high energy state. And the claim is that when we have an attractive interaction, you'll find that constructing the BCS state with that funny superposition of different numbers of particles, it has a non-zero expectation value of phi, and that lowers the energy. So phi really wants to have some non-zero value. And that's another way of saying that BCS state has lower energy than I'm calling it the vacuum, but it's the Fermi C. It's another way, that's a very common picture that you'll see. But these are all just giving you different ways of understanding spontaneous symmetry breaking in different languages. All right, so what are the physical consequences of this Cooper pairing, this spontaneous symmetry breaking? Well, I've got this slide is rather dense. Okay, so if you already know of some of this stuff, this will make sense to you. If you don't know, I'm afraid this is not going to explain it to you from nothing. So I just want to say it to have the summary here. So one thing that you have, if you have an attractive interaction and the ground state is that BCS state, is you have these things called Goldstone bosons. A Goldstone boson, going back to here, corresponds to moving around the bottom of the wine bottle here. See, if you're this state here, there's two directions you can move. You can move away from and towards the middle, and that changes the energy. Okay? You increase the energy whichever way you go, and that corresponds to a massive particle. But you can also go the sideways direction around the bottom, and that doesn't cost you any energy, right? You could be anywhere around the bottom here, and it's all the same energy. So that's called a Goldstone boson. It's a massless particle. It's saying that this phi, the phase of phi, is a massless particle. You can excite it with as little energy as you like. So the existence of that massless particle, that Goldstone boson, arising from the breaking of the fermion number symmetry, that's going to dominate the low energy behavior, right? If you have only a little bit of energy available, then what are you going to make? You're going to make the cheapest, lightest particles. And this guy is massless. So you're going to be able to make that. So that's going to dominate the low energy behavior of the system. And for example, that's what gives you superfluidity. These superfluid Goldstone bosons, these angular degrees of freedom, they give you a superfluid. Another thing that can happen if the fermions are charged, and so they couple to a gauge field, a photon, is that Goldstone boson can combine with the photon, and you can make the photon no longer massless, but massive. Previously, the photon was one of these massless particles that even if you've got very little energy, you can make photons. So it's an important player in the low energy behavior. But if you do this spontaneous symmetry breaking, you think you've got another massless particle, right? We have the photon, we do the spontaneous symmetry breaking. Now we have another massless particle, the Goldstone boson. No, the Goldstone boson and the photon get together and they form a conspiracy and they decide to become one massive particle. So you lose both your massless particles. And that's a superconductor. And then finally, you get this gap in the fermion spectrum. Previously, before you formed this condensate, you could take states just below the Fermi surface and push that particle up above to where there's a hole for arbitrary little energy. Now you can't do that anymore because every momentum mode is being used to build the condensate, right? In every momentum mode, this coefficient here has some non-zero value. So every momentum mode has a little bit of Cooper pair in it. And if you come along and say, I want to make a particle in this momentum mode, you're hitting that with a creation operator here. And as you know, if you know about the anti-commutation relation of fermion operators, this will kill the Cooper pair in that mode. So if you try to make a fermion in some mode, you're like, okay, there's a condensate of Cooper pairs, but I want to make a 200 MeV quark, right? Point going that way. Okay, you make it. You destroy the Cooper pair in that momentum mode, but that Cooper pair was contributing to that nice lowering of the energy, right? Now the energy isn't being lowered so much, so you pay a price. And that's the gap here. This gap here in the spectrum of excitation says if you try to make a fermion with some definite momentum, then you're going to break a Cooper pair, and that's going to cost you some amount of energy delta. So you no longer can you make fermions for free. Okay, the Fermi surface is no longer a nice place where arbitrary small amounts of energy can be used to create fermions. You can't do that anymore. You have to have at least this delta, this gap, which tells you how much Cooper pairing there is. So the result is where previously fermions played an important role in the low energy behavior, transport, now they're frozen out. They cost too much. Okay, if the amount of energy available is less than the gap, they might as well not be there. Okay, this is meant to be a summary, not a full explanation. So I understand that this may have been more understandable to some people than others. But does anybody want to ask a question online or in the room at this point? We're all happy or equally unhappy? Okay, right. Okay, so now I'm going to go specifically to quarks, okay? Up to now, everything I said was very general, right? It could be talking about electrons, Cooper pairing, and making a superconductor. It could be talking about helium-3 atoms, Cooper pairing and forming a superfluid. It could be about any fermions, really. But now let's think about those quarks. Remember, we're up at that high density end of that phase diagram, these crazy high densities. We're in the middle of a neutron star. So we've got a dense system of quarks. They've got an attractive interaction. They want a Cooper pair. Well, what are those Cooper pairs going to look like? Well, the interesting thing with quarks, which I have to be careful if are there any condensed matter physicists here? I should be very respectful about electrons. Electrons are wonderful, but electrons, there's really only one type of electron, right? Neutrons, there's only one type of neutron. But quarks come in many varieties. So just saying Cooper pairing is not enough. There are many choices. So here's a quark-Cooper pair. And each quark, what does it have? It has a spin, okay, which is, I guess, this A index, up or down. It has a flavor. It could be an up or a down or a strange quark. Those are the flavors that are available at the densities that we're typically talking about in neutron stars. And quarks have this color degree of freedom, which is the thing that the strong interaction operates on. And that's three colors, red, green, and blue, we call them. So a quark is not just a quark. You've got to say, is it a red up, spin up quark? Or is it a green, strange, spin down quark, right? There's many choices for what kind of quark a quark is. And that means that if you talk about Cooper pairing here, this Cooper pair has lots of indices, lots of choices. In fact, it's got 3 colors, 3 flavors, and 2 spins, which makes 18 choices for one quark. There's 18 choices for the other quark. So actually, there's an 18 by 18 color, flavor, spin matrix of possible pairing choices. So this is how you can write it. You've got this P thing here, which tells you the structure, which colors and which flavors and which spins are pairing with each other, and then some strength in front, saying how strong is the pairing in this channel, which is another way of saying is how favorable is it energetically? How much does this pattern lower the energy of the system? And the one that lowers the energy the most is going to be the favored pattern. There's only going to be one really, the best pattern is going to be the one with the lowest energy. And the question is going to be, which one is it, right? Because 18 by 18 is a lot. So we'd like to narrow it down a bit. We can narrow it down a bit without knowing really very much at all about the details of the strong interaction, even though it's the strong interaction that's doing this, by using some very general principles. One thing we need to know about the strong interaction is that the strong interaction is most attractive between pairs of quarks that are in a color antisymmetric state. Okay, that's how you build baryons, right? By building a color antisymmetric wave function, and that's got the lowest energy. So red-green minus green-red, okay? That's attractive, very attractive. You can look at it in one gluon exchange. You can look at it however you like. That's the most attractive. So we expect the wave function, the favored wave function for a Cooper pair, to be color antisymmetric. What about the space wave function? Well, in general, you would like to not have anything complicated. You'd like all directions in space to be the same, because if different directions in space are different from each other, then some are contributing more and some are contributing less. And that generally means that you're not going to get the maximum amount of energy. So ideally, you would have what they call S-wave pairing, symmetric in space. Okay, you exchange the two quarks, the wave function doesn't change. Also, what about the spin wave function? Well, again, generically, you don't want to single out a direction in space. You'd like all directions to be the same, because then they can all contribute coherently to the energy. So you'd like it to be isotropic. Isotropic means spin 0, which is up, down, minus, down, up in terms of spin. So that's antisymmetric. So just on sort of grounds of some combination of knowing a little bit about color, about the strong force, and being prejudiced against breaking rotational invariance, you can guess that the favored, most attractive channel, since it's color antisymmetric, space symmetric, and spin antisymmetric, and with fermions, their overall wave function has to be antisymmetric, right? That's a principle of construction of fermion wave functions. The wave function has to be antisymmetric overall. So if it's antisymmetric in two things and symmetric in one, we've got to find one more thing that it's antisymmetric in. And so that the one remaining thing is flavor. So we can guess that the wave function will be antisymmetric in flavor. Things like, strange up minus up strange. And that means you expect pairing between different flavors, because you can't make a flavor antisymmetric wave function between two of the same flavor. Up, up minus up, up is 0. Okay, so you can't have a flavor antisymmetric wave function unless, only if you're dealing with two different flavors. Yes.
I know there's some discussion for P wave superconductors.
Yes.
Is this still possible?
It's possible. I'm just saying this is the naive expectation for the simplest, base version of Cooper pairing would be S wave, spin singlet, color antisymmetric, and then that tells you it's flavor antisymmetric. The other ones are not impossible, and they may even be favored if there's something that stops this one from happening, and that can happen. We'll talk about that, I think, in maybe the next lecture next Tuesday.
So is that, I mean, also interested in that possibility, because as you know, the neutron could become the P wave in neutron.
Yes, that's right.
And is there such a study to that the P wave quark pairing in neutron star is possible?
It's not impossible. It may happen if there's something that disfavors this, right? This is the strongest if it's allowed.
Yes.
But as we'll discuss later on, there can be things that make this difficult. And then something like a P wave may become the best available alternative.
Oh.
Okay, but so I'm not saying no, I'm saying sometimes. Right.
Yes.
So I hope to clarify that as we go.
Yeah, because if the P wave is there, then the critical temperature should be decreased as in the
Yes, that's right.
Then
Well,
maybe it may be affect our transport phenomena.
Right. So the critical temperature being decreased is another way of saying the gap, that delta, is decreased, which is another way of saying it's a less favored channel, right? In general. But there may be, the energy is less, but there may be something that stops this one, and then the P wave can become favored. Okay.
Sorry, I think I didn't follow the spin asymmetry
Right.
the general argument for spin.
It's just isotropy. Like, if it's spin singlet, it's spin 0, so all directions are the same. And that's more symmetric. If it's spin triplet, then it chooses a direction in space. And that means one direction in space, there's sort of more pairing, and other directions, there's less pairing. So in general, what that tends to mean is that some directions are not contributing as much, so the total amount of energy you get is not as much. Okay, this is a sort of Gardner's rule, right? It's not a rigorous mathematical thing. It's a sort of thing that you see in spontaneous symmetry breaking, that generally you only break the symmetries you have to, right? And generally the favored thing breaks the symmetries it has to and doesn't go breaking lots of other symmetries for no good reason. Generically, that's how it tends to go. Okay, so what we've learned here is there are many possibilities for Cooper pairing. Electrons are simple. Spin up, spin down, minus, spin singlet is generally how it goes, and there's nothing else to talk about. right? Only one possible channel. Here, there are many channels, and we have some idea about which one we expect to be favored, but there's still a lot of choice. So let's talk about how we try and sort out what the quark-Cooper pairs are going to look like. So, okay, I'm going to tell you in advance what the answer is, okay? So up here at the very highest densities, that superfluid phase is called the color flavor locked phase, or CFL. And what does it look like? I'm just doing the color and the flavor indices here. It looks like this funny thing with delta functions, or this funny thing with antisymmetric tensors. But if I do it in a more sort of understandable pictorial way here, it's saying the red and green colors are antisymmetric, and they're correlated with the up and down flavors being antisymmetric. And then there's another component where the green and blue colors are antisymmetric, and the down and strange flavors are antisymmetric, and so on. So there's an implicit mapping between colors and flavors, right? We're saying red maps to up, green maps to down, blue maps to strange, and then you make it antisymmetric in those colors and flavors, and you add them up, and that's this wave function. Okay? And it obeys this, it's color antisymmetric, red, green minus green, red. It's flavor antisymmetric, up, down, minus down, up, and so on. Okay? So this is what this state looks like. And it turns out to be the winner under some circumstances at very high densities where you can treat the strange quark the same as the up and down. So where all three quarks look the same, they all look massless. Okay, very high densities, they all look massless, so it's like having three flavors all the same. And under that circumstance, this pattern in that 18 by 18 matrix is the winner. This is the one with the lowest energy. And it's called the color flavor lock phase for reasons that I'll explain in a minute, right? But right now, I show you its wave function, but so what, right? What are the properties of this wave function? What does it do? Any question about? I mean, I just gave you the answer in advance, so it's hard to ask a question.
If you introduce spin, then you have to write more complicated.
Yes, yes. So then each one of these would go with up, down, minus, down, up for the spin. They would each get the same factor. So that's just one factor outside the whole thing, you could say. Right? So you could say this is the color flavor part of the wave function, and then you multiply it by a space part, which is just spherically symmetric, and a spin part, which is spin singlet up, down, minus, down, up for everybody. Right. So I just tried to keep it, yeah, not too complicated, but you're right. That's all there.
So excuse me. Excuse me. So I think that very naive question that so the QCD is the color gauge theory. So that how should we think of the Elitzer's theorem for this condensate colored object?
Right. So this is the same thing that you get in the standard model, right? In the standard model, when you break the SU2 gauge symmetry, your Higgs field is not a gauge singlet, right? So you operate in unitary gauge where you choose a gauge that has the condensate pointing in the same internal direction everywhere in space, and you build your theory in that gauge, and then you calculate gauge invariant observables, and you get the Higgs mechanism that way, right? So this is the exact same thing, but with the SU3 color symmetry instead. So yes, this is the standard story with breaking of a gauge symmetry, where there is not necessarily a gauge invariant order parameter, right? The order parameter that you're dealing with is gauge variant, and you're going to, so that implicitly you've chosen a gauge. In this case, the mapping of red to up is basically a gauge choice, right? Anytime you talk about a color, it's a gauge choice. So this is a gauge choice. We've chosen some gauge. And then if we calculate gauge invariant observables, we will get valid physical predictions.
But do you have the gauge invariant kind of the order parameter for this phase?
So in this phase is a superfluid. So there is a gauge invariant order parameter. It corresponds to the condensation of a dibaryon.
Mm-hmm.
So it's the same operator that you would get if you were looking in a hadronic phase at baryon-baryon pairing. Okay. So you would not necessarily be able to distinguish this phase from the order parameter. You couldn't necessarily distinguish this phase from a phase where hadrons were Cooper pairing, a SU3 flavor symmetric hadronic phase.
Mm-hmm.
Right. As usual, confinement is not, detectable by an order parameter or deconfinement.
Okay.
Did I answer your question okay?
Yeah, okay. Thank you very much.
It's a very reasonable question.
Okay, very dynamic. So here you're saying it's buried at a very high density.
Yes.
Is that mean so if we have this pairing, the free energy of this system is lower than the vacuum, right?
It's lower than if you didn't have the pairing.
Yeah. So my question is it still possible to have the different pairing scheme that has a lower free energy than this case?
Well, the claim is this is the lowest.
Okay, this is.
Yeah, this is the lowest. That's the claim. Okay, so yeah, there's the wave function again. So what does it do? Now I'm going to talk about group theory. So if you understand group theory, this will make sense to you. And I'm afraid if you don't, this may be harder to understand. But I will. I want to say the properties, and that's the language I have to use. So this state is, if you ask what are the symmetries that it breaks and what are the symmetries that it doesn't break? Well, what do you start with? You start with the color symmetry that says the red, green, and blue colors can all be rotated into each other. That's an SU3. And then you have, if you assume massless quarks, you have the left-handed and right-handed separate flavor symmetries. You can rotate the up, down, and strange into each other, the left-handed ones, and separately, you can rotate the right-handed up, down, and strange into each other. So that's two separate SU3 symmetries. And then you have the baryon number symmetry that says you can do a multiply by a baryon number phase. This is the symmetry of the Hamiltonian. Now, after you form this condensate, the remaining symmetry, because remember these condensates break a whole bunch of symmetries, what you've got left is one SU3 that's a combination of you do a color rotation and a coordinated flavor rotation. Since color and flavor are coordinated in this Cooper pair wave function, you can still leave it invariant. If you just do a color rotation, obviously you'll change the color part. If you just do a flavor rotation, obviously you'll change the flavor part. But if you do a correlated color and flavor rotation, you can leave this whole thing invariant. And that's what this SU3 group here is. There's a correlated color and flavor rotation. And the U1 baryon is broken down to a Z2 because there's a pair of quarks that you're creating. So you've got a much smaller symmetry left. If you want to know where electromagnetism is a gauged subgroup of the flavor symmetry here. And there's another electromagnetism, a massless new photon, which is the corresponding U1 subgroup of this leftover color and flavor rotation symmetry here. So if you started off with a massless photon, you still have a massless photon. This is not a superconductor. Right? It changes the photon a little bit, but it doesn't make it massive. However, it is a superfluid. It breaks baryon number conservation. This is a global U1 symmetry. When you break one of those, you get a superfluid. You get those Goldstone bosons, those superfluid phonon modes. So this is a superfluid because it breaks baryon number. It also breaks chiral symmetry. Chiral symmetry is saying you can do separate left-handed and right-handed rotations, but you can't anymore because color is only a symmetry when you do it the same on the left and the right-handed fermions. And so if you want to do a correlated color and flavor rotation, you have to rotate the left and right flavors the same. So this is what they call a vector symmetry, meaning you do left and right together. And rotating left and right separately is not going to be a symmetry anymore. So you've broken chiral symmetry, but not in the usual way. People normally think that it's a quark-anti-quark condensate that breaks chiral symmetry. In the vacuum, when people talk about chiral symmetry breaking, it's a quark-anti-quark condensate. But here is a different mechanism. It's a quark-quark Cooper pair high-density condensate, but it can still do the same thing. It can break chiral symmetry. So you could have the high-density state looking a bit like the low-density state in that they would both break chiral symmetry, but in different ways. As I said, there's still a photon. There's a slightly modified photon. It's a little mixture of the original photon with a little bit of gluon mixed in to make it massless. But it's still a massless photon. So if you ask, what's the sort of summary of what does this color flavor locked quark matter look like? The answer is it's a transparent superfluid insulator. Okay. So the concepts that condensed matter physicists use, oh, sorry, you can't read that on the screen here. Yes, okay, it's interesting. The contrast works on the monitor, but it doesn't work on the projector. So I apologize for that. So it's a transparent because there's still a massless, an insulator because it's gapped. All the fermions are gapped by the Cooper pairing. And and it's still got a massless photon, which can propagate through unimpeded, so it's transparent, but it's a superfluid. So transparent, superfluid insulator. The concepts that condensed matter physicists use to talk about the materials we find on Earth, those concepts are sort of universal, right? This stuff is totally different. It's 14 orders of magnitude away in density and things like that. But you can still talk about gapped or not gapped, meaning insulator or not insulator. You can talk about superfluid or not superfluid. You can talk about can photons propagate freely through it or not, transparent. So there we are. Frank Wilczek called it a diamond as big as the Ritz. It doesn't break translational invariance, those. Okay, so I guess I'm out of time. So I can stop whenever you want. I'll just say a couple of words about how we would be more quantitative here. So if you want to find out which is the favored phase, how did we get to that color flavor lock phase? You need to choose some model of the strong interaction. We've got to have a Hamiltonian, right? We need a Hamiltonian for the quarks, and then we can plug this state in and see is the energy low or high, and we can plug in other states and see is the energy low or high. But once you've got a Hamiltonian, you guess some color flavor spin pairing pattern, like that CFL pattern. You calculate its free energy, and then you minimize the free energy to find out what all those coefficients are in the variational state and what's the size of the gap. You impose gauge neutrality, so it's electrically neutral and it's color neutral. And when you do those things, the pattern with the lowest free energy wins. Now, so that all sounds fine, but I started off with, magic, right? A model of the strong interaction. Well, that's tricky, okay? So how do we model the strong interaction? Well, you can try and do perturbation theory, which is good at very high densities when QCD becomes weakly coupled, but at the densities we're interested in neutron stars, we've only just gone beyond separate neutrons and protons, right? So we're kind of not in the perturbative regime yet, right? The perturbative regime would be way higher densities. So although you can try perturbation theory, there's no real reason single gluon exchange should be dominant. You can try the lattice, right? Then if we want to do non-perturbative field theory, we stick it on the lattice and evaluate the path integral, the hard way by brute force. But it turns out when you go to high density, that path integral that you do on the lattice becomes an oscillatory integral, plus minus, plus minus, plus minus, plus minus, a very jagged function in a million dimensions, okay? Impossible to do. It's very frustrating. We can formulate it perfectly. You can write it on a mug, right, and drink from it, but we can't do the integral. It's just an integral, but we can't do it because it's highly oscillatory and very high dimensional. So for the moment, lattice gauge theory can't help us with high density. High temperature, no problem. The integral is positive definite. Okay, high density, the integral is very horrible. So lattice doesn't help us yet. Perturbation theory is not really valid. People very often use these Nambu-Yonah-Lacinio models. So they take the real horror of what's going on with gluons making gluons making gluons, the strongly coupled QCD, and they say, this is like consider a spherical chicken, right? Let's just, pretend it's a point interaction between quarks. Fine, you can do that, but it's going to be, I think, semi-quantitative would be a charitable description. There are then other ideas. People look at large numbers of colors and postulate the quarkionic phase from pretending that 3 colors is big. And is 3 colors big? Maybe. We don't know. It's an interesting conjecture. Then there's holography, where people construct a gravity dual. Again, it's generally large number of colors. And then there's effective field theory, where you say, okay, I don't have a fundamental theory. I'm just going to start constructing a theory like chiral effective field theory and just have a number of parameters that sort of parameterize my ignorance. So these are different ways people model the interactions between quarks. And this is the sort of background behind the calculations that then people do, try out different pairing patterns, plug them into this, and get the answer. And the answer seems to be, let me go back here, that the NJL model and perturbative QCD, and I think most everything that's been tried, predicts a gap of in the sort of 10s to 100 MeV range for the color flavor locked pairing pattern at the kind of densities we're interested in neutron stars. So, maybe if there's quark matter in a neutron star, it could be in this color flavor locked phase. Okay, is that a good time for me to, I can skip some slides and go to my final slide. Would that be a good thing to do?
Yeah.
Okay. All right. So I'm going to skip over some slides here where I talked about, relating it to neutron star phenomenology, but that's okay. We can talk about that another time. Oops. So let me talk about what would we like to do in the future. So I didn't talk about the different ways in which you might try to learn about high density phases from astrophysics, but they involve measuring properties of neutron stars. So it's not too surprising. The one thing that would help us is more data about neutron stars. And the sort of things that can be helpful is measuring their masses and radii, measuring their spin and age simultaneously, which tells us how fast they spin down, measuring how glitches go, measuring their cooling, measuring their temperature and age, and we'd like to know their mass too. And also, most recently, the sort of new kid on the block is measuring gravitational and electromagnetic signals from neutron star mergers, which we hope could also give us some insight into the properties of the matter that those neutron stars are made of. So what more data is one ingredient we'd like. Since we're talking astrophysics, though, modeling comes up. That we're doing modeling in order to compare predictions with data, with observations. You're modeling neutron stars and mergers. So you'd like merger simulations to become better, more reliable, to include more of the physics, to be able to show you what happens if things like there's a phase transition, or how to transport properties or dissipation in the nuclear matter or the quark matter, how do they affect the observable signatures of a neutron star merger. You'd also like to understand better how other things that we measure work, like what's going on with glitches or other phenomena, like maybe X-ray bursts or something like that, things that might be affected by the material properties of the matter in the star. We'd like to have good astrophysical modeling of them. Also, these things called R modes that I didn't get to talk about, but okay, we'd like to model them better. And then we'd like the pure theory. So we've got the data, we've got the modeling, and then there's the pure theory side that for the theorists, we would like to understand the properties of high density matter better. So that color flavor lock phase is the very highest density phase, but neutron stars are not very high in that sense. They're sort of medium high. So what sort of phases would we expect at lower density? Is it possible that it's one of those other phases, maybe the P-wave pairing, could become favored when you're at medium density? And I'll talk about some of that in my next lecture next Tuesday. You might ask, can we model QCD? Okay, one gluon exchange is not a good model, but maybe there are other things, functional renormalization group or Schwinger-Dyson equations, where you sum up families of diagrams, and maybe you can find an intelligent way of doing that that captures the relevant physics and gives you a good model that you could use to predict the phase diagram. Ultimately, of course, what we'd like, the holy grail in this subject, would be if that sign problem could be solved and we could do the same thing for high density quark matter that we already do for high temperature quark matter, namely calculate its properties on the lattice. And there isn't, it isn't solved yet, but there are examples out there of systems that if you look at them in one way, they have a sign problem. One example is the Z3 Potts model, which if you formulate it in the standard way, has a sign problem and you think, oh no, this is a disaster. But then there's a clever reformulation in terms of different degrees of freedom, and then the functional integral can be formulated in a way that doesn't have a sign problem. So there is hope that for specific systems, some of them may have special recipes that allow them to be done in a brute force functional path integral fashion. And our hope is that some very clever, young probably person, will find a reformulation of QCD that allows us to do it on the lattice, and then many of these questions could be answered. Thank you very much.
Thank you very much. There must be questions. Yeah, please go ahead. Yes.
Yes, maybe I'm missed. So do we have some very intuitive expectation that if we have the more gluon the contribution, so how the CFL will, be changed on?
Well, so in the color flavor lock phase, the gluons become heavy, right? This is the standard story with spontaneous breaking of a gauge symmetry, just like the W and the Z become heavy and the photon stays light. here, one gluon photon is light and the other gluons become heavy. So they become an octet of vector mesons, basically. Okay, so they're there in the theory. I mean, something like, they're not exactly the gluons, but they're the gauge invariant content that corresponds, if you like, to the gluons. There's some vector mesons that have a mass, and so if you have enough energy, you can excite them, but they won't play a big role in the low energy behavior because they have a mass gap.
So you have mentioned the complete analogy between condensed matter physics. I wonder whether the relativity is important or not.
Not so much. Yeah, so if you're doing high density matter, then there's already a favored reference frame, right? Which is the reference frame in which your matter is stationary, right? So
You can neglect antiparticles.
yes, generally, right? Exactly. You can neglect antiparticles. I mean, yeah, okay, so that's okay. Yes, that's one way of looking at it, right? Right. So relativity doesn't play such a big role. There's antiparticles are only one manifestation, right? But on the whole, the material itself gives you a reference frame, and then you operate in that reference frame. So the dynamic, again, the Hamiltonian is relativistic, but the state that you're starting with has a natural reference frame. Mergers. So in a neutron star merger, they see temperatures up to about 80 MeV. Not all of it, some of it's cooler. They see a range of temperatures. I think in one of my later lectures, I'm going to show you some data on that.
So when you say transparency, I confuse a little bit because in the usual superconductor and then the normal metal, I mean, normal metal is not transparent, right?
Well, some phases are, right? If the charge degrees of freedom are gapped, so anything that would couple to a photon is gapped, then it will be transparent, right? It's if you've got low energy charged excitations that can absorb a photon. I mean, I'm imagining a low energy photon, right? I mean, there's also, exciting photons can excite things across the gap between the valence band and the conduction band in a.
Okay.
But I mean, I'm thinking of the lowest energy, like radio waves. Radio waves go through because they're low energy and they can't. Right.
And yeah, maybe one. You have, yes, please.
So very naive question. So in condensed matter physics, people are looking for room temperature superconductivity. So I wonder, is there any possibility to look for color superconductivities at lower pressure, lower temperature?
Yeah. Well, so I mean, you remember we went at the very beginning. I showed you that picture of the neutrons and protons overlapping. Unfortunately, if the neutrons and protons aren't overlapping, you're not going to get quark matter. Now, what you will get is perhaps proton superconductivity, right? So, you've got the neutrons and the protons, they're both fermions. So at nuclear density, you can get neutron-neutron pairing, making a superfluid, and you can get proton-proton Cooper pairing, and they're charged, so they give you a superconductor. But then again, that's at nuclear density, when you've got a liquid of protons, right? I'm afraid at our ordinary room temperature, the main thing we get is liquids of electrons. And so you'll have to come up with some other thing, to have a liquid of, which I know is difficult.
Oh, yeah, great.
Well, I'm not in this field, so I may be asking something else. But this color flavor law in phase. You wrote this levitator and levitator, and one of these is
I can go back to it. Hang on.
Yeah, it looks like something that has both color and flavor in this field.
Yes.
That's the expectation of it. It is
right. So yes, exactly. So this thing here it has 2 color indices and 2 flavor indices because it's got 2 quarks in it, right? Each with a color, each with a flavor. And it's anti-symmetric in the 2 colors and anti-symmetric in the 2 flavors. And this N here is the same.
Yeah.
So, you know, the red, green, it's like red, green, and then 3 here, and up, down goes with 3 here, right?
Yeah.
So yes.
But it looks like this, the first Leviturator alphabet is taking care of the color.
Yes.
The other one is taking care of the flavor.
Right.
And one contracted seems like each one of the index of each Leviturator contracted seems like suggesting that something that has both indices have vacuum expectation value.
Well, yes, it's creating a correlation.
Right.
It's creating a correlation. There is no natural correlation. So it requires some arbitrariness, right? That we're just choosing that, you know, that blue will correspond to strange, right? That 3, color number 3 and flavor number 3 are correlated. If we think of these as integers, right, alpha, beta, then they're saying 3 and 3 are correlated. But which color is 3? Which flavor is 3? So it's arbitrary.
Right. Yeah, but some so this is kind of like a spontaneous symmetry
It
breaking.
is spontaneous symmetry breaking. Yes.
Is there some like concrete thing that has that?
Yes.
On this?
Yes, this thing.
Yeah.
So, okay, this gets back to the question earlier. So this thing here, this quark thing, has a VEV if you allow yourself to operate in the unitary gauge where you sort of give it a VEV. Okay, so if you don't worry about gauge invariance, the answer is yes, it has a VEV. Okay, I don't know if you want to worry about gauge invariance, but
Not right.
okay, so good. So suppose we don't worry about gauge invariance. This guy, I mean, that's why I drew these angle brackets around it here, right? This is exactly the guy that has a VEV.
Right. But this is like particular way to get the bed, right? This
Yes.
this-
Okay, so let me answer what I think you might be getting at. If I change the mapping between colors and flavors,
Okay.
that will also have this VEV. And that change corresponds to one of those flat directions in the wine bottle, right? That all these, any way of mapping colors to flavors, that's this leftover SU3 symmetry. This leftover symmetry is saying you can map colors to flavors any way you like. Those will all have the same energy. So it's saying there are these degenerate, equal energy, different ways of constructing this VEV, right? So there's a whole bunch of flat directions in the energy landscape that are all equally valid. And this, I've just picked a representative here. I think that might be what you're getting at, that this is not unique. There's a whole bunch of them.
So can you have something like this delta I alpha, delta J beta? That there is no minus. So there is anti-symmetric.
That would be anti-symmetric. That would be a combination of symmetric and anti-symmetric.
Right. I see. But I'll think.
Okay,
Thank you very much.
sure.
About this, the CFL is a ground state of the matter, at least at super high density. That you showed from this symmetry kind of argument for the energy minimum. But there was some discussion by Thomas Schaeffer and others using renormalization group argument, and that must be a ground state. Is it
At very high density.
very high density? So
Yes, I
need
think-
to prove?
That's a good, I don't know. There are mathematicians around these parts, and so I'm not going to use the word proof, right?
Oh,
I think, yeah. I think to the degree that physicists regard a question as settled, then yes, the argument is that that channel is the most favored channel at very high density, where you can treat the QCD interaction as weak.
yeah.
But the structure of the interaction is the one gluon exchange that tells you that color antisymmetric is favored. And yeah.
As far as I remember, they start from one gluon exchange at
Yes.
super high density, and
Yes.
there are all kinds of different pairing pattern
Right.
with some coefficient, and then try to calculate some flow of the
Right.
each coefficient, and then see.
Right. Right. And that confirms this. Right. Right. Absolutely. Yes.
Okay. Yuki Fujimoto,
yes, thank you. Thank you for a nice talk. So I have a question regarding the modeling the interaction. So I actually have two. So you mentioned that in perturbation theory, you cannot it neglects the instantons, but can you can't you include that by including that by some, I don't know, dilute gas approximation or something like that?
Yes, yes. So in fact, I mean, the next thing I have on there is the Nambu-Lonicinio model. And one way people do the Nambu-Lonicinio model is they include in that an instanton vertex, right? A vertex that has that flavor antisymmetric left to right property that instanton vertices have. So you can include it. You can, with an NJL model, you can have a vertex that's based on one gluon exchange, if you want. You can add in, you can construct any model you like. So you can combine those ingredients. I agree. Yes.
Right. Yeah. And the second question actually is related to that. So in a perturbation theory, the instanton is instanton induced interaction is much weaker compared to the one gluon exchange interaction. But however, if you go to lower density, then in NJL model you have a quite strong instanton induced interaction. So what is a qualitative mechanism that somehow enhances this instanton contribution?
I don't know. Let me think. Do I have any ideas? No, I don't think I understand why that happens.
Okay, I see.
The instanton, if you use an instanton-based interaction, you still get the same result as far as what's the favored phase.
I see. Yeah, that's true. Yeah, I see.
Okay, there are questions from the Zoom, just the text. So Lucas, Troyer, okay, I just read.
Yes.
What about the curvature, GR contributions?
Okay.
Are these also negligible even at very high density center of the neutron star field?
Yes, I guess it was there and then it disappeared. Oh, there it is. Oh, okay, good. I can read it on the screen here.
Yeah.
So yes, so I'm talking about these phases being in the middle of a neutron star, and you're thinking, well, a neutron star is highly general relativistic and has curved space and all that kind of thing. So why don't I worry about that? And the answer is that as far as material properties go, I can sit in the locally co-moving frame of the material and talk about its properties, calculate its microscopic properties, and then it's up to the person doing a simulation of a neutron star merger or the person implementing this in the TOV equation or something. It's up to them to sort of make the transformation to whichever reference frame they want to use for the material. Okay, but if you're talking about microscopic properties, the simplest thing to do is always discuss them in the co-moving frame, and then it doesn't matter as long as the size of the typical volume that you're talking about is smaller than the scale over which the curvature varies. That's fine, and that's true because in neutron stars you're talking about kilometer scale variation, and in the case of strong interactions you're talking about femtometer scale interactions, right? So I think it's safe to just imagine yourself in the co-moving frame and somebody else later on will slot this into some curved space-time. Does that answer you?
Okay, yeah.
Okay.
And then Motoi,
Tachibana?
yeah. Can you speak up or maybe can you read?
Okay, so he says analogy between the Higgs and color superconductivity, but there's a big difference. The vacuum in the standard model is perturbative, while the one in QCD is not. Okay, well, that's true. So, right. I mean, let's see. Yes, I'm just trying to think if that makes a big difference, which is your question. So, okay, so certainly the way that we treat the standard model, where in we think of it perturbatively because the weak interaction and the electroweak interaction is weakly coupled. It's all 1 over 137 or 1 over 120 something for its coupling. So it is all weakly coupled. So we can do that in that case. So yes, we've got a Higgs phase, which is understandable perturbatively. So we can do it there. I think, yes, you're right. The vacuum state of QCD is confined, which is not perturbatively understandable. That doesn't mean that there can't be a Higgs phase. The claim I'm making is that there is a Higgs phase at high density where this diquark field gets an expectation value. Now, you may not be able to distinguish that Higgs phase from the strongly coupled confined phase at low density. That's true. But if you go to high density and the theory becomes weakly coupled, I think then it makes sense to talk about a Higgs phase. I don't know if I've answered your question. I think as long as I'm not trying to draw conclusions about low density, I'm fine. The low density phase is different. It's strongly coupled and confined, but I'm only talking about high density, so maybe I'm okay. I think that's my answer.
Your knees are wrong. Naoki Yamamoto just he made a comment on instanton induced interaction. It's essential to make the positive parity ground state favorable. Yeah.
Yes, okay. One gluon exchange, yes, you're right. One gluon exchange has additional sort of symmetries and degeneracies that on its own won't tell you that, right? Fair point.
So you just a little bit shield the potential to the
Right.
parity direction.
Exactly.
Okay. Any other question from the Zoom audience?
Excuse me, can you hear me?
Yes.
I have a question about finite temperature case. And I remember that if one introduce a gluon fluctuation, then the order of the second order phase transition from the mean field results turns out to be first order. Do you know the recent understanding of this?
I mean, I thought that was a fairly old result.
Is that old? Uh-huh.
There are recent, I mean, I don't know of any recent change to that.
Uh-huh. I see.
leak.
Okay. Thanks.
I think that would still apply here as far as I know.
Okay. Yeah, the question. Okay, so if not, is it possible for us to get your the slides?
The PDF, yes.
Okay, yeah. So that we can share.
Sure.
For the next lecture, we can study.
Study, yes, that's what you want.
Okay, very much. Thank you very much. Yeah. 3:30 next week, Tuesday.
Yes.
Remember that Monday is a holiday in Japan, right? The next week.
Okay. Let's see now. Now I need to kill my Zoom stuff.